Alright, 3-5 is exponential and logarithmic models. So what we're going to do is we're going to take the equations that we've come and the graphs for exponents and logarithms, and we're going to put them into some applications, use them for some real-world models. So there are 5 different types of models we need to be able to use in this section. Exponential growth we've seen before. That's the one that's taking off. We've seen that. Then the exponential decay is the one that's coming in for the landing from a high initial point. And then we're going to see a couple different models. The Gaussian, logistic growth, and the logarithms we've actually seen before as well. Remember the ones that look like this. So let's take a look at what they look like. And so again, the first two, the exponential growth and decay, we've seen before. Gaussian is what a lot of you may have seen as a bell curve before, and it's going to be centered on 0, centered on the y-axis there if there's no transformations. We have our logistic growth model down here, and so that's a situation that starts to increase a lot and then flattens off. So there are situations where initially we grow a bunch, but then that growth slows down. And then the last two that we see here are for your logarithmic models. The first one for natural logs, and then for log base 10. So that's what we're looking at in this section. So let's start our first example. It's going to be an exponential growth model that's talking about how much advertising is spending. And they give us an equation here. They say that S equals 10.33 E to the 0.1022t, and they say that 7 has to be less than or equal to t less than or equal to 11. And they ask us, all right, according to this model, and this model is what we came up with based on these numbers here. According to this model, when will the US spend 40 billion on advertising? So we're going to say, all right, let's find out. We're going to put 40 in here, and we'll have 10.33 e to the 0.1022t. And so our job is to solve for t, figure out how long it will take to get to 40. So step 1, let's divide away. Divide by 10.33. Okay, and if we do that, we're going to end up with e to the 0.1022t, and about 40 divided by 10.33 is roughly 3.87. I should use the curlies here so that it's approximately. All right, and now the key to all these problems is getting rid of the e. How do we get rid of e? Throw the natural log in front of it so that the natural log and e cancel, and we end up with the natural log of 3.87 is equal to 0.1022t. And we'll plug the natural log of 3.87 into our calculator. We'll divide both sides by 0.1022. And if we do it all right, we're going to get approximately 13.2. So it'll take a little bit more than 13 years for this to happen. So when will this happen? Well, we don't want to just say 13 years from now. We want to say 13 years from 2007. So 13 years from 2007 is 2020. 7 plus 13. So sometime in 2020, we would guess, remember this is just an estimate, we would guess that that's the year we'll end up spending $40 billion. All right, so that's our example. See if you can do something with problem 43. Pause the video, give it a shot, and I'll be back with the answer when you're done. All right, for part A, they give us our equation, and I'm going to go ahead and use the graphing calculator on this one. So let me flip it over and get the graphing calculator up. All right, so let's come up with our equation here. I'm going to clear this out. And we are saying that our equation is negative 18.5 plus 92.2 e, which is second natural log, of 0.0282 t or x in our case. And so I'll close my parentheses, and there's our equation. Now, first things first, it asks us to fill in the table here, and it says that 1970 is year 0. So I'm going to let the calculator do that for us here. We're going to say, we're going to use the table, and we're going to start our table at 0. And in this case, I'm going to start counting because it says 1970. Then if I look back 1980, 1990, 2000, I'm going to count by tens. And go to our table. All right, so here we go. In 1970, we spent 73.7. In 1980, 103.74. In 1990, 143.56. And then in 2000, 30 years, 196.35. But how about 2007? Well, that's a little trickier. So, well, not trickier, but we need a different starting point. So let's start in year 30. And then count by ones. So we can get in there and see 37. And so 37 is 243.24. So we would have our tables all the way filled in there. All right, so let me flick back over here. And we're saying, all right, according to the model, when will the population reach 300,000? So this is where we're going to go in, and we're going to use our equations. Now remember that we're counting in thousands here. So 300,000, we're just going to write down 300 equals negative 18.5 plus 92.2 e to the 0.0282t. All right, so first thing, I'm going to add the 18.5 and get 318.5, and I'm going to divide by 92.2 to get e by itself. All right, and now how do we get e out of there? We're going to go natural log of both sides. So we'll end up with natural log of 318.5 over 92.2 equals, oh, I lost my clicker, come back, equals 0.0282, running out of room, t. And so we'll divide both sides by that 0.0282 to get t. If we do all that right, it comes out as approximately, where'd my answer go? I've done this once already. Approximately 43.95. All right, so remember, we're guessing how many years this is going to take. We're going to say not round down to 43. We're not going to truncate. We're going to round. And so we're going to say 44 years. We're going to guess it's closer to 44 than 43 years. So if we had to guess, we would say 44 years from 1970, which would take us all the way up into the year 2014. So that would be our answer for A. Now, the key here on B is, do you think that this model is valid for the long term? Well, let's go back and look at what a graph of this would look like. So I've got my y equals here. Let's come up with a good window range here. So our x's is going to be the years. So 70 is 0. We don't care about anything before that, so I'm going to put 0 in for my x min. And we went up all the way to 2014, 44 years. So I'm going to say a little bit more than that. How about 50 years? The minimum population, the smallest thing we saw in 1970, if I go back to my table and look at that again, the smallest amount was 73.7. So don't need to go any smaller than that. So we'll say 70. And the largest amount that we got, if we were in year 37, was 243. So, and you can see it jumps up pretty quickly after that. So I'm going to say 300 for my high end. And let's go ahead and graph this. And this is taking off, and it's getting exponential. It's growing faster and faster and faster and faster. So the question then becomes, do you think it's feasible for the long-term predictions to keep going and getting taller and taller and taller and taller? No, it's not valid. There's no way for our population to keep growing that fast. At a certain point, we'd be growing faster than there are people in the whole world. So we can't sustain that kind of growth forever, but in the short term, we can have exponential growth.